Welcome back to the Daily Dean. Has every other explanation for what a Newton is and everything physics related failed you? Have no fear, because I am here explaining Newtons with a high schooler, right? Ooh. So basically, imagine if you own a Chromebook, you know how much it weighs. A Chromebook weighs about 2 to 3 pounds, right? If you needed that kind of reminder, wow, you don't measure your Chromebook's weight? No, I'm just playing. So if you have this idea of what it feels like, imagine we're in space, and this thing is totally floating, without me holding it. Basically, it weighs 1 kilogram. Now, if I applied a force to it, we can measure how much force I apply, or quantify, give it a number, give it a value, by saying it as 1 Newton by saying my push has 1 Newton of force, or my pull. It doesn't really matter whether it's a push or pull, but we're gonna say we're pushing my Chromebook along with 1 Newton of force. Basically, it's the same as saying there's 500 milliliters in this water bottle. Dasani is gross. I wouldn't recommend drinking it. And saying that there's 40 units of power in your phone. Same idea. We can increase the value of our force, saying there's 2 newtons or 3 newtons of force in my push, but it doesn't really matter, not yet. So, say that I'm applying 1 Newton of force to this 1 kilogram object. It'll start accelerating by 1 meter per second per second. What that means is, as I constantly apply this force, the speed of this object will increase every time I measure it. So say here, it's stationary, right? Here, and then after 1 second, it's at 1 meter per second. It's speed. We take a screenshot of time and see how fast it's moving. After 2 seconds, speed will be increased again, and we take another screenshot, and it's at 2 meters per second. The same idea applies to gravity. Now, this is where a lot of explanations for the Newton tend to fall short. Gravity pulls something down, just like how I, push along my Chromebook. And I just realized I should have talked about this as well. If you have a heavier object, if we have 2 Chromebooks stacked side by side together, it'll require twice as much force, right, to move at the same speed. So if I had 2 kilograms of Chromebook stacked side by side and I tried applying the same force, it'll only go twice as slow. It'll only go half as fast. Now, if I wanted to keep it moving at 1 meter per second squared, 1 meter per second, I need to apply 2 newtons of force. Now, say if I wanted to move it twice as fast, 1 kilogram of one Chromebook, and I want to move it at 2 meters per second squared, meaning after 0 seconds it's at 0 meters per second, after 1 second it's at 2 meters per second, after 2 seconds it's at 4 meters per second, right? I would need to apply twice as much force to the Chromebook constantly. What that means is 2 newtons of force could move this twice as fast. Now I want you to notice that really we're just multiplying 1 kilogram by the acceleration, 1 meter per second. The amount of force it requires to push 1 kilogram object 1 meter per second is just 1 times 1. The amount of force it requires to double that is just 1 times 2. See? So basically, the force that I am pushing it is just the mass by the acceleration. That's where we get force equals mass times acceleration. But this is where we can talk about gravity. This is where it gets really fun. This object, this battery, weighs about 102 grams. That's 3 to 5 ounces, about. So, say that, this battery is being pulled by this little leather mask, and it's exerting a force downwards that I can feel as 1 Newton. You know why? Because the acceleration of Earth is 9.81 meters per second. As an object falls, it gets more and more speed, and it'll increase how fast it's going. If we took screenshots of how fast it's moving, after 0 seconds, it's at 0 meters per second. After 1 whole second, it's at 9.81 meters per second. After 2 whole seconds, it's at 18.5, because the speed doubled, or it would be 19.5. Its speed doubled from, 9.81 to 19.5 or whatever, and so on and so forth. As each second passes by, the speed grows each second, 9.81 meters per second. Now, because we're multiplying the acceleration of gravity and the mass of this battery, we find that because the acceleration is faster than if it was just moving 1 meter per second, its force will be the same if we just lower the mass, right? So since this is lighter than the Chromebook, but moves faster than the Chromebook, they both have the same force. They would both, same forces, right? Because instead of the force being horizontal, it's actually just downwards. Because remember that I applied the force pushing the object, right? I was pushing it along this way, back and forth. But this way, it's going downwards. So the force is just in a different angle. And this is where, once again, where I said a lot of explanations tend to fall short, because we think about forces being, down, left and right, horizontal, instead of up and down, which is what a Newton is in, earth feelings and whatnot. So you basically, in Newton, you just multiply the mass of your object by the acceleration, and that's the amount of force it's exerting. To reiterate, to summarize, it'll take 1 Newton of force to push this along every second, and increase its speed 1 meter per second, but it'll take, 100, this object exerts 1 Newton of force downwards, because it's 102 grams multiplied by 9.81. If you have calculators, you can do that yourself. 9.81 times 102 grams is 1 Newton of force, and it'll apply to other scenarios. If this object weighed 130 pounds, that's about 50 kilograms. 50 kilograms multiplied by 9.81 is 490 newtons. So I exert a force downwards of 490 newtons. And that's the explanation for what a Newton is. And, oh, you know what? I totally forgot to talk about James Prescott Joule experiment. But this is a good explanation, and I hope you learned something. So, find out next time on what is James Prescott Joule and why do I want to talk about him. Don't look it up. It's cool. Now, bye. Hope you learned something.